This is one of a series of lectures from the Further Mathematics Support Programme looking at revision. In this lecture we're looking at Edexcel FP1 specification, and in particular looking at the unit on proof. The specification from Edexcel for proof talks about proof by mathematical induction. There are other questions which have proof by other means, but the main section of the specification is for induction. There are four types of question that you need to be familiar with. The first one here, looking at the proof of some of the standard formulae for summation. The actual use of these is covered in another lecture, another revision session for series. So those one first type. Second type, looking at questions about divisibility. Is a particular expression divisible by a number? Finding general terms of sequences, so proving that in a particular sequence of numbers is produced by a given formula. And then questions involving matrices. So if you're familiar with the multiplication of matrices, then we can look at some particular questions proving things about matrices with induction. The idea, of course, of proof by induction, it quite often uses analogy of a row of dominoes. We start off by proving the what's called the base case, where in fact that something is true for n equal to 1, or sometimes for n equal to 0. So it does depend on the question whether you're looking at 0 or 1, or even perhaps another number. But we're starting with the showing that the expression is true for the first of the dominoes, whatever that might be. And then on the assumption that it is true for the kth value, so this would be n equal to k here. So the fact that that one is true, we show that then produces the truth of n equal to k plus 1. Now, of course, once we've done that, then this knocks down the whole series of dominoes, because if we know it's true for n equal to 1, and then it's true for n equal to k plus 1 if that is true, so it's then true for 2, and hence for 3 and 4 and so on all the way down. So in fact we've then got it true for all values of n. So that's the idea of proof by induction. So there are essential parts that we need to show in all proof by induction cases. That is the base case, where we've got our first value, and then the what's called the inductive step. If it holds for some value of n, then it's true for the next value. Normally we use n equal to k, and that then shows that n equal to k plus 1 is true. So if that is true, that implies that this is true. And all these bits then go together, and then we get the final statement at the end. So we need all of these elements to pick up the marks in an exam question. So going back there to our slide, we're going to look at some exam questions on each of these. So I'll do one exam question on each type of proof. So the first type is proving one of these standard results for series, in this particular one for sigma r cubed. So we take the first of all the base case, and that's when n equal to 1. So what we're saying then, of course, is the sum from r equals 1 up to 1 of r cubed. Well, that's just 1 cubed, which is 1. And our formula that we've got to show, 1/4 multiplied by 1 squared multiplied by 1 plus 1 all squared. So that gives us, of course, 1/4 of 2 squared, which is also equal to 1. So it's true for n equal to 1. We then assume that it is true for n equal to k. So assume true for n equal to k. And then we need to look then at the formula for r equal to 1 up to k plus 1 of r cubed. Well, that will be the sum from r equal to 1 to k of r cubed, and then plus the next term, which is r plus 1 cubed, all cubed. So there we've got the statement that we can go on and prove now, because we're assuming that this first part is true, and so this is equal to 1/4 of k squared and then k plus 1 all squared, and then finally we've got plus, when r is equal to k plus 1 all cubed. So in that line above should have been k plus 1, the next term. Going on from there then, well, in all this sort of proof, similar to the ones that you may have seen in series, if not, then do look at the revision session on series, and you'll see that in this sort of expression we always factorize out as much as we can, and here the factorization comes to be 1/4, and we can see that there's a common term of k plus 1 all squared. So if we take out that and see what we're left with, well, in the first part, obviously left with k squared, and in the second term we'll have k plus 1, that's giving us the k plus 1 cubed in the line above, but remember that we've taken out the quarter as a factor, so this is 4 times k plus 1. Well, we're almost there now. This is then 1/4 k plus 1 squared. This is, in the square bracket, k squared plus 4k plus 1, and of course that is 1/4 of k plus 1 all squared, and then in the square bracket we've got k, I beg your pardon, that should have been plus 4 in the line above. In this bracket then we get k plus 2 all squared. Now, to write it in the form that we want, we should really be writing it as k plus 1 plus 1. So I'll just rewrite that as 1/4 k plus 1 all squared, and then in a bracket k plus 1 plus 1 all squared. So then that's our formula with, instead of n up here, n squared, n plus 1 squared, we've now got it as k plus 1. So here we've proved that our formula is true for n equal to k plus 1. So as if we assume that it's true for n equal to k, we've then shown that it is true for k n equal to k plus 1. So we've shown true for n equal to k plus 1 if true for n equal to k, and also we know that it's true for n equal to 1, and therefore it's true for all n integers n, and positive. Right, so that final statement there, you need to get all the elements written in to pick up the marks. Well, let's look at the mark allocation here. The 5 marks, the first mark is what's called a B mark, so B1 here. just for the base case. There is another B1 awarded at this line here, and then a method mark for the factorization of that bracket there. So a method mark for getting that correct, even if you don't get the accuracy mark. Once you've got down to this stage here, there's an accuracy mark for doing the correct algebra to get to this expression. And then the final accuracy mark, as I've already stated, is for making sure that you've got all of these elements here in the proof. So this statement at the end is vital to pick up that final mark. So there we are, the 5 marks allocated to that particular question. The second type of question is one of looking at sequences and formulae, and again the process is exactly the same. We must go through all of these. So the base case, n equal to 1, we can say that u1 is equal to 2, and u1 in our other formula is equal to 5 to the power n minus 1 plus 1, so this should be un there. Un equals 5 to the power n minus 1 plus 1, but of course when n equal to 1, 5 to the power 1 minus 1 plus 1, that's 5 to the power 0, so that's equal to 5 to the power 0 plus 1, which is equal to 2. So really just for showing that we've got 1 plus 1 there is equal to 2. So it's true for n equal to 1. The inductive step, then, we assume that it's true for n equal to k. And we look at uk plus 1. Now uk plus 1, using the formula up here for un plus 1, is equal to 5 times uk minus 4. But we know that UK, or we're assuming that UK is given by the formula, so that we can say that that's equal to 5 times, then UK is going to be 5 times k to the power, rather, k minus 1 plus 1 minus 4. But that, if we multiply out the bracket, that gives us 5 to the power of k, and then plus 5 minus 4. But writing that then, so that we're clear that we've got k plus 1 in here, this is equal to 5 to the power of k plus 1 minus 1, and then plus 1. So here's our formula now, true for n equal to k plus 1. So it's true for as if it's true for n equal to k. But we know it's true for n equal to 1. So therefore it's true for all n. Which are positive integers. Okay, so there we are, looking again at where the marks are allocated. this time only 4 marks. There is a B mark just for the base case here, so 1 B mark here. A method mark for using the truth of n equal to k to then substitute that into the formula for k plus 1. Getting down to this stage here, an accuracy mark, and then again an accuracy mark for this final statement with all those elements in there. So the 4 marks to give you the that finished question. The final question I want to look at then was from June 2011, and in this one there are 2 different proofs by induction. The first one using matrices, and the second one looking at a divisibility type proof. So again, the idea is always the same: basis case followed by inductive step and then your statement at the end. So I'll do these 2 obviously separately, and we'll look at where the allocation of the marks. You know, it's again 6 marks, so each of these induction proofs is getting 5 or 6 marks normally, and these are being combined in one question to give you a longer question giving you the 12 marks. So looking at these one at a time, the first part of this is the matrix. Well, again, the basis case when n equal to 1, then obviously the left hand side of that statement there is a matrix 3, 0, 6, 1, and the right hand side is equal to 3 to the power 1, 0, 3 times 3 to the power 1 minus 1 and 1, which of course is equal to 3, 0, 6, 1. So it's true for n equal to 1. If we assume it's true for n equal to k, then we need to, on the basis of that, show that 3, 0, 6, 1 to the power k plus 1 is given by the same formula. Well, how do we do that? Well, we look at that being equal to the 3 to the power k, the matrix for 3 to the power k, so it's 3, 0, 6, 1 to the power k multiplied by 3, 0, 6, 1, the matrix. So the 2 matrix multiplications, it doesn't matter which order you do this in actually, so there are 2 variations. However, I'm going to do it in this order, but we're going to assume that truth of the first matrix being given by excuse me, 3 to the power k, 0, 3 times 3 to the k minus 1 and 1. And we're multiplying that by the matrix 3, 0, 6, 1. Well, this is just a little bit of matrix multiplication, obviously. So remember that we're taking the rows of the first matrix and using matrix multiplication to combine them with the columns of the second matrix. So the elements here are going to be 3k multiplied by 3, so that's 3 to the power k plus 1, and 0 times 6, so that's it. The second element on the top row is going to be 0 because we've got 3k times 0 and 0 times 1. The element on the bottom row is 3 times this and then plus 1 times 6. So this is the more complex one. It's 3 multiplied by 3 times 3 to the power k minus 1 and then plus 6. And the final element comes out to be 0 and 1 times 1 is 1. Sorry about the lining up there. Now we need to calculate what these are equal to and express it in the form that we want. Now the top line is already there, 3 to the power k plus 1, 0. This expression we can write as 3 times, we take the 3 into here, we'll get 3 times, and then we've got bracket 3 to the power k plus 1 minus 1. And then finally a 1 in that element there. So just checking that out. From here we've got negative 9 plus 6 giving you the negative 3. So there's the negative 3 in our bracket. So there's our matrix then, written in the form that we want. So it's therefore true for n equal to k plus 1. And then that final statement to get your mark saying that it's true for n equal to k plus 1 if true for n equal to k, and it's true for n equal to 1, and therefore it's true for all n that are integers, positive integers. Again, that final statement is necessary to pick up all your marks. Where do the marks go here? Well, there's, as usual, a B1 mark for the basis case, an M1 mark for the induction step starting off correctly, and then an accuracy mark for getting that multiplication at this stage. As long as you've got that, then there's a dependent accuracy mark here, so that you've actually done the matrix multiplication correctly. And then finally, sorry, not quite finally, an accuracy mark for doing that multiplication and simplifying it, and the final accuracy mark for this inductive step, sorry, the statement at the end of your proof. Right, the second part of this question then was the final type of induction proof that we need to consider. That is one of divisibility. The same process, n equal to 1, so the base case, n equal to 1, then we get 7 to the power of 2 minus 1 plus 5 is equal to 12, which is obviously divisible by 12, so it's true for n equal to 1. The second part, the inductive step, can be done in several different ways. So what I'm going to do is do 2 of those, which I think are probably the most likely ways that you will have been shown. So they're both similar in that we must assume that it's true for n equal to k and prove it's therefore true for n equal to k plus 1. Now the first method involves taking f of k plus 1 and subtracting f of k. And therefore that we will get 7 to the power 2k plus 1 plus 5 minus 7 to 2k minus 1 plus 5. So that's our formula there. Putting in k plus 1 into there. 2 times k plus 1 minus 1 is 2k plus 1. And 2k substituted into here gives us 2k minus 1. Well, combining these, obviously the 5s are going to cancel out. So we get 7 to the power 2k plus 1 minus 7 to the power 2k minus 1. We can factorize out of that 7 to the power 2k minus 1, leaving us with an extra 2 powers here, so 7 squared from the first one, but we've taken out everything of the second term there, so minus 1. And this is 48, so this is 48 multiplied by 7 to the 2k minus 1. Or in other words, it's 12 multiplied by 4 times 7 to the 2k minus 1. And hence, it's equal to 12 times something. Let's call it p. Now that's for our difference of the terms, but we want to show that fk plus 1 is divisible by 12. So just rearranging then, fk plus 1 is equal to 12p plus f of k. But both of these are divisible by 12, and therefore we've got the truth of f plus k plus 1 is divisible by 12. And then our final statement, as before, it's we've shown that fk plus 1 is divisible by 12, assuming that it's true for n equal to k. So let me just write this at the left hand side here. We know that it's true for n equal to k plus 1 if true for n equal to k, and also true for n equal to 1, and therefore it's true for all n in z plus, which is what we're asked to find in the question. So that final statement. The mark allocation, very similar here to the ones before that we get, and I won't go through it fully, but we've got the basis case, actually I should basis case here, and then allocation of method marks and accuracy marks as before. The method mark, accuracy marks coming into here, and then finally two more, a method mark here and a final accuracy mark, and then one for the final statement. So the 6 marks allocated there. Right, so that is that one done by one method. What I'm going to do now is to look at an alternative method for this inductive step. I'm not going to do the full question again, but there is an alternative step. So here we are as the alternative for the inductive step. We're assuming it's true for n equal to k as before. So in other words, we can write 7 to the power 2k minus 1 plus 5 is equal to 12 multiplied by something. And then if n is equal to k plus 1, f of k plus 1 is equal to 7 to the 2 k plus 1 and then plus 5. Sorry, 7 to the 2k plus 1 minus 1 in there, and that's equal to 7 power 2k plus 1 plus 5. Now that, if I factor out of here the power of 2 to the 49 this time, that's 49 multiplied by 7 to the power 2k minus 1 plus 5. Now this is where we can use the line that we had, this truth statement here, because this 7 to the power 2k minus 1 is equal to 12 times something, 12m, minus 5. So this is equal to 49 times 12m minus 5 plus 5. And if we now work out what that comes to by multiplying out the bracket, we get 49 multiplied by 12m. So I'm going to write that as 12 multiplied by 49m. So I want to leave that 12 in there to show that we've got the divisibility. And then the numerical term, 49 multiplied by 5, negative 5 rather, and then plus 5 comes out to be minus 240. But of course now I want to take out that factor of 12, 49m, and then 12 is a factor of 240. So there we are, we've shown that if it's true for n equal to k, it is therefore now true for n equal to k plus 1, because this is divisible by 12. So that's an alternative induction step. Okay, that's the end of this revision session. If you're interested in this and that one was useful to you, then there are others available online for the other sections of FP1 and all of the other further maths courses with Edexcel and indeed other boards.